Hello everyone. Today we are talking about low-rank modeling of third-order tensors. Firstly, we need to introduce what is low-rank modeling. Please look at those pictures. As is well known, so in MATLAB, each picture is represented by a matrix, and each pixel in the picture corresponds to an element in the matrix. Now, if we look at those images, we can see this image is, for example, this image is very symmetric. You can see those columns of the image are highly correlated. And if we consider this image, and this is a Chinese character, you can see this character is very symmetric. And of course, the human face is very symmetric. And you can see this is also very symmetric. This is to see that it is obviously that those images has global symmetry. Now, if we transform, for example, this image into a matrix, so the columns of this matrix are highly correlated, and some columns may be identical. That means this matrix representing this image is of low rank. That is, its rank is much smaller than the number of columns. So if we consider this image to be a high-dimensional space, we know it has a low-rank structure. That is, what we want to do is to pursue the low-dimensional structure in the high-dimensional space. Robust principal component analysis of image data was introduced by Candice Ma Yi and John White. So this is a very useful technique to recover the low-rank structure of this image. That is, for example, if we look at this image, we can see there are lots of sparse noise in this image, and the background is very symmetric. That is to say, the background is a low-rank matrix, and the purpose of the robust PCA is to recover this low-rank matrix of the original matrix with sparse error. For example, if we look at this video sequence, we can see this is a camera video for example, in the Carbondale Mall. We know that the building, this store in the mall is unchanged. It may remain the same all the time, but the people are moving around, so the people are changed. The people, always change. That means for those persons can be considered as sparse error in this image, and the background of this image is symmetric. That is, the background is a low-rank matrix. So for this video sequence, each time we have an image, and this image has is 144 times 172 pixels. So we can use the width multiplied by the height, and then we can transform this image into a vector column of a big matrix. And then if we perform robust PCA on this matrix, we can recover the log-rank approximation of the original image plus the sparse error. Okay. So you can see this technique, the RPCA technique can recover the log-rank structure of the video sequence plus a sparse error. Subspace clustering is also a very useful technique, and this clustering technique is different from the traditional clustering methods. Well, everyone knows that it is well known that the k-means clustering method is very popular to group the data into several different clusters. Points in the same cluster are very similar, and points in different clusters are very different. However, the subspace clustering is to cluster data into multiple subspaces using the geometry of the clustering. Here we assume that the points are coming from a union of subspaces. Now, why we need to consider tensor? Now, for example, for this grid level image, you can see we can use a matrix to represent this image, and each pixel corresponds to an element in the matrix. However, if we look at this video sequence, you can see we have several images because we have another dimension, which is the time. So for those kind of data cube with a dimension bigger than 3, so conventional data representation using matrix is not sufficient. That is, we need to consider such kind of high-dimensional matrix, which is a tensor. Now take this color image for an example. We know that this image has different color. That is, it has another dimension, which is 3 channels. Therefore, we can use 3 matrices to represent this color image. The third dimension are the 3 channels. Okay, so color image is a third order tensor. Now, for this facial image data, we can see it's not a good idea to use a matrix to represent those images, to represent this facial data set, because it has different features. It has several features, which is the expression, people, illumination, and views. So it's better to use a tensor to represent this data set. People use different methods to study different aspects of tensor. Mainly speaking, there are 3 aspects. One is the theory. That is, we use the multilinear algebra, algebraic geometry, and high-dimensional statistics to study the properties of tensor decomposition. For example, is identifiability or some other properties. And people coming from applied background using convex optimization or non-convex optimization to study tensor decomposition. And the people coming from computer science, they use tensor to study computer vision and image processing. So tensor research gives us better results, much more better results. Now, as is well known, the matrix SVD is very useful to do matrix analysis because it has a deep relationship with the principal component analysis. Now, for a third-order tensor, Kummer and Martin proposed a new tensor singular value decomposition. So their opinion is that a third-order tensor can be viewed as a matrix of tubes. That is, a third-order tensor can be decomposed to the T product of three tensors. The tensor in the middle is a diagonal tensor, and the tensor in the right are orthogonal tensors. So this is a picture of tensor SVD. Tensor SVD is very useful because it needs not only process the matrix SVD, but also can remain the Lorentz structure as it transform the tensor into the Fourier domain. So this is our basic theorems. That is, we want to consider the approximation of a tensor X using a Laurent tensor. We want to obtain Z, with a Laurent. And as is well known, the rank Z is NP hard to compute. So we can use the Shattan P norm or log determinant norm to approximate rank of Z. Traditionally, people use the nuclear norm traditionally for a matrix, people use nuclear norm to approximate the rank function because the nuclear norm is the lower convex envelope of the rank function. However, it has been noticed that the nuclear norm is not always good because there's a gap between the nuclear norm and the rank Z. Because the nuclear norm is to take the summation of all the singular values, and the rank Z is to count how many singular values we have. So this was pointed out to us by Fazil Merriam and Stephen Boyd. Those are very famous mathematicians. So it's better to use another approximation of the rank function. We use the non-convex rank approximation because it can better approximate the rank of the tensor. We take the baby example of a vector x, of a value of a scalar x. We know that if x is a scalar, so the rank is 1. Okay, no matter how big x is, the rank is 1. If we use the nuclear norm, then this is a linear function. It is a linear function. So when the x become very big, this nuclear norm become also very big, but the rank remain the same to be 1. That means there's a big gap between the nuclear norm and the rank. And if we use such kind of logarithm, then it can shrink less the singular value, Okay, and we can also use the x with a power smaller than 1 to shrink less the singular value. Shrink less the value. So we can see when the singular value is very big, then the non-convex approximation works better. Now this is our results to solve this objective function. To solve this optimization problem, we transform the original problem into the Fourier domain. That is, the original tensor x is transformed to a x hat in the Fourier domain, and then we solve those, and then we solve this objective function in the Fourier domain, and then we take the inverse Fourier transform. Okay, this theorem is very useful. For example, for the tensor RPCA problem, a tensor RPCA is instead of recover a low rank matrix, we need to recover a low rank tensor, and we can use some non-convex function to approximate the rank of the rank of the low rank part of the tensor. Okay, and this is our Lagrange function, and we can use ADMM algorithm to solve this optimization problem. Okay, and so this is our experimental results. For example, this is a starfish, and this is the original starfish. It's a color picture, and this is crafted image. So we can recover the low rank part of this crafted starfish and get rid of those kind of sparse error. You can see our results are very good. Now we talked about the subspace clustering before, but now people can group the image data into a tensor like this. Okay, we can group the image data into a tensor. And then, according to different views and different features, okay. And after solving this kind of self-representation objective function, this Z is a low-rank tensor with a block diagonal structure. So we can, if we recover, if we solve the Z, then we can like this, if we have a tensor data, and then we solve and then we obtain the self-expressive tensor Z, then we can we can use geometry, to compute the graph Laplacian, and then we do the multi-view clustering. On this data set, you can see our results is very good. Our result is very good. In the future, we will do more and more applications. For example, background and foreground separation in video. And we need to do more research on theory and algorithms about non-convex optimization. Thank you.